Welcome everyone to this session on using Akka Streams with Java. My name is Jacek Kunicki. I work at Software Mill. We are a software house based in Poland. There are two special things about us. First of all, we have no office at all. And secondly, we have a completely flat and transparent structure. If you'd like to learn more about how it works, just catch me after the talk. So today we're going to talk about stream processing. Now, I think that most of you have like a general idea of what stream processing is. So basically, you have some source of data that produces your data. You have a target for your data, so you can call it a consumer, for example. And you have a number of stages that do some kind of processing to your data. And of course, there is data flowing from the left to the right. So what is special about reactive streams and about the reactive approach to stream processing? Well, in this scenario that you can see on the slide, there may be a problematic situation because, well, you can imagine two scenarios. First, when the producer is slow and the consumer is fast, there's really no problem because, well, the consumer can do its work and will never be flooded with data from the producer. But if you imagine the opposite scenario where the producer is fast and the consumer is slow, there is a danger that the consumer is going to be flooded by data. And then the consumer needs some way to deal with it. It may, for example, drop the excessive data as it happens, for example, on the lower level in hardware, for example. But there are also other ways to solve it. And one of the ways to solve it is called back pressure, and this is what is used in the reactive approach, and this is like the most important idea of the reactive manifesto. So back pressure is basically a way for the consumer to signal demand to the producer. So it is the consumer who tells the producer how much data it can accept, and the producer is forced not to send too much data so that it doesn't flood the consumer. Now, what you see in the slide is some general terms for its general naming. Akka Streams, which is one of the implementation of reactive streams and about which we are going to talk today, has its own naming. So the producer in Akka Streams is called a source. This is a source of data, so something that produces the data. Then the consumer is called a sink, so this is where your data ends. And the intermediate stages where the data is processed are called flows. And the source with flows and with the sink all together form a graph. So what we are going to build today are processing graphs for our data. So the stream processing landscape is like pretty big. I mean, there is a lot of technologies around stream processing. Here is a slide from my colleague's talk about an introduction to big data. And you can see that Akka Streams is even not there among the other stream processing technologies. So what is special about Akka Streams? Well, first of all, it's theoretically not distributed, unlike Spark streaming, for example. Now, this is not entirely true, because in Akka Streams, we have the implementation or the runtime of the stream processing is decoupled from the definition. So we have a DSL for defining how our data is going to be processed, but then we have the actual runtime. And and actually you can use any runtime you'd like. There is a default one based on Akka actors, but there is an API that lets you create any runtime called a materializer for Akka Streams. And actually, there was like an initiative a year ago to build a materializer based on Apache Gearpump, which is one of the distributed processing engines, so to say. But as far as I know, it never came to life. So there was some beta version, but actually, when you look at Akka Streams today, the only way to run it is the default materializer, so the default runtime based on an actor system. So it may be distributed. If any one of you wants to write their own materializer, you're free to do so. But so far, the only available one is the default. When defining the processing graph, you basically build a recipe for processing the data, and you create small reusable building blocks that you can write them once and use it in different graphs, for example. It's important that all the building blocks are lazy until you actually run them. So what you create is just a recipe. There is no processing happening, actually, until you explicitly run the entire graph. And, well, if you've heard about Akka before, you may have thought that this is like a Scala library. But surprisingly, most of the Akka users, specifically the Akka actors part, are using Java, and that's why Lightband decided to, well, they are doing really good work to keep the Java API usable, because, well, Scala gives you more possibilities in terms of like some magic that happens behind the scenes, but there's also a good, nice Java API, and I'm hoping to show it to you today. So our use case that we'll be covering today is some kind of data importing scenario. We basically have a number of gzip CSV files that we want to do some grouping operations in the meantime, and then store it to some kind of database. I chose Cassandra because, well, this example is taken from a real life project that we realized using Akka Streams actually. So it's Cassandra. It could be anything else. In the gzip files, if you look at the slide, we have lines that have an ID and some kind of a value, and for every ID there are two lines. Each of them can have either a valid value or an invalid one. And what our application would be doing is taking each of those two lines, sharing the same ID, then trying to average them and store the average value to Cassandra. And in case when one or both of the values are invalid, we'll also want to handle that somehow gracefully. In our case, it would be some default average value that would also be stored. Okay, so let's get to the I hope most entertaining part of today's talk, so the implementation. So we are starting with, we'll be writing a CSV importer. This is just like a normal class. It has some dependencies. One of them is the actor system that you can see here, because as I said, the default runtime that we would be using is the actor-based materializer. So we would need the actor system at some point. We have some config and we have some reading repository. It's our interface to Cassandra. The details are not relevant at the moment. It basically has a save method that executes asynchronously and saves the data to Cassandra. So the first thing we need to implement is the logic for parsing the lines. So we get a line from a CSV and we will want to convert it to our domain model somehow. This would not use anything from Akka Streams so far, so this is just like plain asynchronous Java code. So we're going to define a method that will be asynchronous, because in the reactive approach, it's about non-blocking as well, not only about back pressure, but also about not blocking. So we're going to be as asynchronous as possible. So our asynchronous method is going to return a completion stage from Java util concurrent of reading. And reading is our domain model. If you have a look at it, it's an interface that says that every reading has an ID. We can have a valid reading that apart from the ID has a value, but we also represent in our domain an invalid reading that just has an ID for the sake of being able to handle the invalid lines gracefully in the future. And it's going to be called parse line. And of course, we're taking a string with a line to parse. So to execute the code asynchronously, we'll be using the completable future and the supply async method. So what we do now, we start by splitting the line by the semicolon to get the fields. Now we're going to take the first field and extract the ID. So we're going to say parse int on fields 0. It's going to be our ID. Then we're going to extract the value, which will be a double. So it's a value. And in the happy path, it should be enough to return our domain object, the valid reading, with the ID and the value. But you can remember from the slide that the lines can also be invalid, and we want to handle them gracefully and emit invalid reading if the line was invalid. So normally we would use a try catch, but I'd like to show another approach, how we can do, for example, a try and catch in a more functional way using waiver. If you're not familiar with waiver, which was formerly called Java slang, it's a library that introduces some concepts from functional programming to Java. So, for example, if you used to program in Java, then you wrote Scala, and then you're coming back to Java, it may feel more natural to use waiver because like the concepts there are a bit similar to what you can do in Scala, for example. So let's instead of returning the valid reading, return a try, and this is a try from waiver. To the try, we need to supply the code for that we want to try. So in our case, it will be parsing the double value. Then we need to map it to an object that we actually want to return. So if the conversion was successful, we want to return the valid reading. We can also want to do some logging when the line was invalid. So in our case, we're just like getting the exception and logging that something was invalid. And we also want a default value in case of failure. So when there is a failure, we are logging it first of all and then returning a default value. And in our case, it would be an invalid reading with just the ID. Now it almost compiles. The reason why it doesn't compile is that the get or else expects an instance of what was defined in the map line, so here. So since in the map we have a valid reading, the get or else also expects a valid reading, but we want to return a reading, so what we need to do is to cast the reading here, the valid reading to a reading, and then the compiler is happy. So this is the, I think, simple logic for parsing the line and handling invalid lines. As I said, it didn't include any Akka Streams related code yet, but we're going to start using Akka Streams right now. So when processing our files, since once again we don't want to block, so we won't be loading the entire files into memory. We'd be rather streaming them as a stream of bytes. And having a stream of bytes, if we want to extract lines from it, we need to somehow split the stream of bytes by the new line characters, and then emit some other strings of bytes, emit another byte that represent our lines. So from like generic stream of bytes, we want to have sequences of bytes, each of which represents our line. So we need a line delimiter for it. And in our case, since now we are starting to use the Akka Streams APIs, the line delimiter is going to be a flow. The flow has three type parameters. First is the input type, so it's the type of flow, as you remember, is the processing stage. So it has some input, it has some output. So in is the input type, out is the output type. Flow can also have something that is called a materialized value. And materialized value is the value that is visible to the outside world, because in the input and output are only visible to they are defined in terms of the graph. So those are types of data that are flowing between the graph stages, and the materialized value is something that we can emit to the outside world. Normally we won't be using it in most of the flows here, but there will be one case when we are actually going to use the materialized value. So more details will follow. So in our case, the input type of this line delimiter is going to be something called a byte string. It's basically an Akka type for a sequence of bytes. The output type is also going to be a byte string, because we're going to be consuming bytes from the file and then splitting them by a new line and emitting sequences of bytes that form a line from the file. And since we are going to ignore the materialized value here, we're going to use a special type called not used. So you may wonder why not just use void. Well, the reason is that Akka is both a Java and Scala library. And in Java, to represent something that we are not using, we have the void type. In Scala, we have a unit type. And basically not used is something that ties those two types together. So this is a common abstraction for Scala's unit and Java's void. And moreover, it tells you what the intention is, so that you are not using something. So and we need a neat name for a variable, of course. So to do that, what we want to do is called framing in Akka Streams. So we have a stream of bytes and we want to extract some frames with a delimiter. So this is a built-in, something that is built in Akka Streams. We need to provide a byte string that is going to contain the delimiter. So in our case, it's going to be the new line character. We need to specify the maximum length of the line that we'll be processing. So our lines are pretty short, so 128 is a reasonable default here. And also we have a third parameter called framing truncation. It basically says what we want to do with a line that doesn't contain the delimiter. So if for example, the last line in our file doesn't contain a new line character, we also want to handle it normally. And that's why we set the framing truncation to allow. If we set it to not allowed, it would explode on a line that doesn't contain the delimiter. So that's the first flow we have written. It's pretty simple. It just takes a sequence of bytes coming from the file, splits them using the new line character, and emits another sequence of bytes, each of which is a single line from the file. So the next thing we want to do, and actually use this line delimiter for parsing the file. So we're going to build another flow whose input is going to be a file and whose output is going to be a reading, so the reading from our domain model. And once again, we're not going to use the materialized value. We'll ignore it. So we only care about the data that's flowing like between the elements of the graph we're building. So now when constructing flows, we can use the static method in the flow class called auth, where we provide the type. We once again provide the type of the input element, so that like the compiler is happy afterwards. So in our case, we're going to build a flow of files. And now what we want to do. So for every file that arrives to our graph, we're going to create a source in terms of Akka Streams graph, so something that is emitting elements. So for every file, we're creating a source of lines, actually of readings that come out from this file. So in our flow, when for every file we create a source, we're going to end with multiple sources. And what we want to do is take the values from all the sources that we built from the files that we are processing, and then concatenate them and emit them downstream. It's important that we concatenate them and not like somehow merge randomly, so that we keep the order of the lines. Since, as you remember, we'll be calculating averages, so we need the line with lines with the same IDs to arrive like subsequently. So for turning a source like a number of sources and flattening it, basically flattening it to be able to emit it downstream, we use the flatmap concat method. Well, the name may be confusing at the very beginning, but if you think what it does, it basically takes a number of takes a source, which is like a number of elements, then flattens it to be able to emit it downstream one by one. And concat here means that the elements are from the subsequent sources are emitted one by one, and the order is kept. They are not mixed anyhow. There is also a flatmap merge variant that does some random merging, but it may not preserve the order, so it's not relevant in our case. Okay, so for every file, what we need to do first is create some input stream to be able to read the files. Since our files are gzipped, we'll create a gzip input stream that wraps a file input stream from our file. It's going to be our input stream. And now what we will return, as I said, would be a source of the readings that come from the file. So now we need to take this single file, like this single input stream, and use the code we wrote before to turn the bytes from the file into our domain model. So we have a helper class called stream converters. It has a from input stream static method that takes a factory or basically something that returns an input stream. And what we want to do now? Well, first of all, this is a source of, if you check the type. Oh, okay, it's a source of byte strings. So when we have a source of byte string, we need to like pipe it through our line delimiter, which is a flow that takes a byte string. So to connect the source to our flow, so to our processing stage, we use the via method, and we just say via line delimiter. This gives us a source of byte strings, and the byte strings already represent the lines in our file. Now we may want to be able to drop some lines from the file. For example, if one of the lines contains a header, for example, that we want to skip. So we can use the drop method. We have a configuration parameter that tells how many lines we want to skip. And now, since we have byte strings, but then on the other hand, we have our parse line method that takes a string. So we need to convert the Akka representation of a sequence of bytes, which is the byte string, to a normal string, like a Java string. Unfortunately, this is a built-in capability of the byte string. So we can just call map and use the UTF-8 string method from the byte string that just converts the sequence of bytes to a string. And then the last thing we want to do, and we want to do it asynchronously, is for every line that we have already represented as a string, call our parse line method. So to execute the logic in parallel, we have a map async method that takes two parameters. First, it takes the parallelism level, so basically the number of it's not the number of threads, not always the number of threads, but it's the number of parallel executions of the method we're going to provide. So we have a configuration parameter for non-IO operations, those that don't require file system access, database access, things like that. And we're going to just call the parse line method here. So to sum up what we've just written, we have a method that we have built a flow that accepts a file. For every file, it generates a source of byte strings, so source of sequences of bytes that we then want to convert to our domain model, so to a reading, and emit them downstream in a flattened fashion, so one by one. And then having multiple sources concatenate, multiple sources, we want to concatenate them and not merge. Hence, we're using the flatmap concat method here. So the next thing we want to do, having the readings, we want to compute the average. So we'll be taking, now what we'll be doing is taking pairs of readings and averaging them by ID. Of course, in the meantime, you would need to detect the invalid readings and just throw them away. So we're going to define another flow. Now, this flow takes a reading and emits a valid reading. So even if both lines are invalid, for example, we want to be able to emit a dummy value, so a dummy average value downstream, represented by a valid reading. We are always going to have an ID, since even an invalid reading has an ID. So if we are not able to compute the average value, we'll just use a default one. So, but anyway, we'll be emitting valid readings now. And once again, we're not going to use the materialized value so far. So we're just focusing so far on the internal communication between the graph elements. So the method is going to be called compute average. And once again, we're using the flow class and the static of method to create a flow of readings. And now, what we want to do now, first of all, we want to have groups of readings. We want to groups of 2. So we use the grouped method with an argument of 2 that will give us sequences of readings, and that will have 2 readings. Then what we want to do is execute another computation asynchronously. So the logic for computing the average will also be asynchronous. So we used the map async method previously, but here we are going to use another variant of it called map async unordered. The difference is that in the map async method, the computations are executed asynchronously with a given parallelism, but the results are emitted in the order in which the input elements arrive. So the order is preserved. Map async unordered, on the other hand, starts the computations asynchronously, but emits the value downstream as soon as it's ready. So it may not preserve the order. And in the previous method, where we are emitting the lines from a file, we wanted to keep the order so that the lines with similar IDs are next to each other. But here we don't care about the order of the readings since well, they are already, let's say, merged or averaged. So the order in which we emit them downstream doesn't really matter. And of course, the unordered variant is faster, usually, but you need to be able to ignore the order. The signature is the same, so we have a parallelism level. And we provide some async method that executes the logic. So in our case, we're going to have a sequence of readings. Readings. And execute some code for it. So our code, since once again we're asynchronous, will use the completable feature supply async. And now what we are going to do, we are once again going to use waiver to process the list of readings in a neater way that we would be able to using just Java collections. So I'm going to use the list type, but this is not Java util list, it's the list from waiver. It has a factory method that takes an existing sequence of elements, so it's readings. And now, the first thing we want to do is only take from the pair of readings, only take the valid ones. So, well, we need to do an instance check. And then, since we want our list to have to be of type list of valid reading and not just list of reading, we need to change the type, because here we have the list filtered, but it still contains any readings, and we want to contain just valid readings. So we need to do a cast here. The next thing, having a list of valid readings, is to extract the value from those. So we'll use another map to extract the value. And then what is useful, well, like the implementation of average is trivial, so everyone could write it themselves, but the waiver list already gives us an average method that returns an option. So if the list was empty, we get an empty option, and if it was non-empty, we get an option with the actual result. So on an option, we can call get or else to provide a default value. So if the sequence was empty, so if there were no valid readings in the pair, then we return a dummy value of -1. Otherwise we have the actual average. So this is going to be our average variable. And now what we need to do is emit the average downstream as our domain object as a valid reading. So since in the readings list, the one here, we had two readings, be it valid or invalid, and so we are certain that the first of them contains an ID. Since both contain an ID, so we are safe to just extract the ID from the first reading on the list. And we'll use the average as the value. So once again, in this flow, we have readings arriving. We want to group them in groups of 2. Then in each group, we do filtering and mapping to valid readings. If after filtering we have any valid reading, we average it. Otherwise, we take a dummy default value for the average. And then we emit the value downstream as our domain object as a valid reading. And we are safe to take the ID from the first reading, because that's why we introduced a domain model in which every reading has an ID. Okay, so now let's see how we can, so we have some building blocks ready. Let's see how we can combine them, because, well, of course, our processing of a single file would consist of 2 stages. First, of parsing the file, and the second stage would be computing the average. So if we don't want to use those two flows that we created separately, we can merge them or combine them to create a single flow that we will be able to use afterwards. So now we're going to create a flow whose input is a file and whose output is a valid reading. And the materialized value is once again not used. And it will be called process single file. And what we're going to return here, well, it's once again a flow of file And then we are just saying via parse file, and then via compute average. This way we have combined the two flows, so the two building blocks that we defined before, into a single building block. That is once again a flow, so it has an input and an output, but the types have changed. And you can see here that like combining the flows is type safe. So the compiler guards us against connecting building blocks of incompatible types. So if I change the order of lines here, it wouldn't compile since the types don't match. So even at the compilation stage, we are guarded against connecting blocks with incompatible types. Now the last thing we need to do, so we already got to a point where we have a stream of valid readings that are ready to be saved to the database, so we need to save them. And saving will be done using the reading repository we have. And for saving, we are not going to define a flow, since saving is like the last part of our processing pipeline. So it won't emit anything downstream. So we're not going to use a flow here, but instead a sink. So sink, as you remember from the introductory slide, is the last element of the processing pipeline. So it just has an input. It doesn't have an output. So if you look at the type parameters, it's exactly as expected. So we have a type for the input, and we still have a type for a materialized value, and this time we are actually going to use the materialized value. Why? Because we want to be able to wait until all the elements are processed and stored to the database. So the materialized value of this sink will be some representation of an asynchronous computation. So in our case, it's going to be a completion stage. So that's what we use in the Java concurrent processing. And we would be able to do some like blocking operations on it. So it's a representation of the fact that the processing has been finished. So the input type of our string is going to be a valid reading, and the materialized value, the one that we want to be able to get. So once again, the materialized values are something that is emitted to the outside world, and we'll be able to like get hold of it and use it somewhere. And now we're going to use another abstraction for Java's void and Scala's unit, which is called done. It's similar to the not used type that we have used before. But done, like the purpose of creating yet another type, which basically does the same. So it like abstracts Java and Scala APIs that are different. But once again, it's the reason for creating another one is to like tell you what the purpose is. So the purpose of not used was to signal that the materialized value is not used. And the purpose of done is to signal that basically something has finished. We don't care what the result was, but we just care about the fact that the processing is done. So we'll start creating the thing by creating a flow, once again, that accepts valid readings. And what we want to do now is to asynchronously save those values to the database. So we're once again going to use the map async unordered method, this time with another level of parallelism, since this is an I/O operation, so perhaps you want to use different number of threads in order not to kill the database or for any other reason. So we have a configuration parameter called concurrent writes, and we call the reading repository save method. As I said, the logic inside is really not important here. It basically takes a valid reading and returns a completion stage, so it's an asynchronous computation. And now it doesn't compile since we want a sink. So to be able to actually turn our flow into a sink, we can connect it to some existing sink and fetch the materialized value because we are interested in it. So we are going to use the toMat method, so which means to means connected to something, and mat means give me the materialized value. Since in our case we don't care what the result was, we just want to know that the processing was finished. We're going to use a special built-in sink called sink ignore, which ignores the result of the computation, but it returns, as you can see from the types, a completion stage of done. So that's actually what we're interested in. So it will tell us when the processing was finished, but will discard the results. And you can see that it still doesn't compile. The reason it does not compile is that we need another parameter. And why? Let's get back to the slides for a second. So in the slides, you can see that with the toMat operator, we're combining two things. First of all, we're combining a flow, and on the right-hand side, you have a sink. Each of them can have a materialized value. So the flow has a materialized value of M1, and the sink has a materialized value of M2. And when combining those two using the toMat operator, we need to specify which materialized value are we interested in, so that the materializer knows where to extract the materialized value from. And for this, we have the keep class with some handy values. For example, right, left, both, and none. In our case, we'll be using right, since we want to take the value from the sink, so the M2 value. If, for example, we wanted to take the materialized value from the flow, we would use keep left. We are also able to say keep both, which will return like a pair of materialized values. And we can also use none, which will skip both of the materialized values. So once again, we have a flow to the left, we have a sink to the right, and we're interested in the materialized value from the sink, so from the right. That's why we're going to use keep right to extract, to tell the toMat combiner which value to take. So once again, we have now we had a flow of valid reading, a stream of valid readings. For each of them, we executed an asynchronous code that stores the readings to the database. And then we connected it to a sync ignore, which basically ignores the result, but signals when the processing is completed. And we used keep right to tell the combinator which from the materialized values to choose. So now we're ready to put all the building blocks together to actually build the entire pipeline and execute it. So now we're going to create a normal method that would actually be run. It will be no more a graph stage. And this method would return a completion stage. So that's why this is like our handle to the processing pipeline. And this is what is returned by our sink, the process single files. Sorry, the store readings sink. So the return type is going to be completion stage of done. And we're going to call it import from files. So what we do now is, we want to list the contents of the directory that we want to import from. I'm once again using the waiver list. And we have a configuration parameter, import directory, we call list files, to get a list of files. We'll do some logging. We'll record the start time so that we can measure how fast it is. And then what we want to do, well, now we're building the entire pipeline. So as you remember, we start with the source, then we connect some intermediate stages called flows, and we end with a sink. So to start with the source, we can use the source from method that just takes an iterable, so we can pass the list of files here. Now we have the source. It's time to connect the processing pipeline. So we're going to use via and the process single file flow. And that's why we combined the file parsing and the average computation into a single flow called process single file, so that now we can use it, we can just use a single via call. Of course, we could use two via calls here, and we could say via parse file, then via compute average, but we wanted to indicate that this is actually like our entire processing, and the one big flow for processing our data. So we combined it into a single method. And now we want to execute it. So actually connect it to a sink, and then be able to wait until the processing completes. So normally we could use the to method to connect our graph to a sink, and then we would be able to call a run method on it. But since this is something that you do very often, I mean, you connect the graph to a sink, and then you wait for the materialized value. There is a method that combines the two behaviors, and it's called run with, and it takes a sink. And actually, looking at the types, you can see that the type of the sink is not a sink, but it's a graph with a given shape. So graph is basically an abstraction for every part of the processing pipeline, and it has two properties. It has a shape, and the shape can be a source, a sink, or a flow, depending on the number of inputs and outputs. And you have and it also has a type for the materialized value. So this is the second one. So here we are able to provide, and actually our sink is a graph with a sink shape. So we are able to provide it here. It was called store readings. Then we want to somehow handle the processing results. The when complete it comes from the completion stage, so we are like back to the Java APIs. And now we can see it still doesn't compile. Why does it not compile? Well, as you may remember, what we have done so far is only a recipe for processing our data. So we haven't specified how this is actually going to be run. And to tell the framework, to tell Akka Streams how to run it, we need a second parameter called the materializer. So it's the actual runtime that will execute the computations. And as I said previously, we are going to use the default materializer based on an actor system. So we'll use the actor materializer create, and here use the reference to an actor system that we had as a dependency to our class. So now, well, you may think it's everything, yes, we would be able to run it. It would process the files, but you can notice that what we are doing here is processing the file like one by one. So we take the first file, extract the readings from there, and then pass them downstream. But we would like to be able to process a number of files in parallel, so that we're not reading the files into memory, so we can open a number of streams from the files and basically have some kind of load balancer that basically takes takes a number of files and then executes a number of computations in parallel. And the computations are actually executions of our flow, the process single file flow, then somehow merges all the computations and emits the results downstream. So we want to create a kind of a load balancing stage whose types will be the same as those of process single file. So it would take a file and emit a valid reading actually, but inside it's going to load balance the work across a number of workers. So we're going to write a simple load balancer ourselves. Sorry. Okay, I wanted to create a new class, but okay, just give me a second. Okay, so I think the presentation mode is against me in IntelliJ. So let's just restart it. Okay, it's not only the presentation mode. Sorry for that. Let me just maybe quit IntelliJ and start once again. Okay, back to life, hopefully. Let's just delete those. Okay, one more try. Yeah, Java class. So we're going to call it the balancer. And what we need here is some factory method called create. And it's going to, well, once again, we're going to create something that, like, from the perspective of the shape in Akka Streams, resembles our process single file. So it would be a flow that has an input value and an output value. And as you've seen before, the flow is actually a graph with a shape of a flow. So we're going to be a bit generic. So we will define generic types for input and output. And the return type of our method would be a graph that is going to have a shape of a flow, so a flow shape with the input and output types. And we also need the type for the materialized value, and it's going to be not used here. And we're going to take two parameters. First is the number of workers. So it's the number of parallel computations that we want to execute. And then we need to have the actual logic that is executed as a worker. So in our case, it will be a flow with types in and out and the materialized value of not used, called the worker. So now to create our own graph, we're going to use something called graph DSL. So we have a graph DSL and create method. The create method gives us access to an instance of a graph builder. And builder is basically something that allows us to manipulate the structure of the graph. So the first thing we want to add is a built-in balance stage that basically balances the work across a number of workers. And the second thing we would want to add is a built-in merge stage. So those are we are taking two built-in stages called balance and merge, and then like adding them to our custom graph. So we're going to say builder add, and this is a balance stage. We call the create method, and it basically takes the parameter saying how many outputs the balance stage is going to have, because the balance stage has a single input and can have a number of outputs, and this is the number of workers is the number of outputs that we're going to have. We're going to call it balance. In the same fashion, we're going to add a merge stage with the type of out. And also then the number of, this time the number of inputs, which will be the same as the number of outputs from the balance stage. Now you may think whether it's verified in any way that the number of inputs and outputs match. And actually it is, but it is done in runtime by the materializer. So if you for example didn't have a matching number of inputs and outputs, and actually if you left and if you tried to connect an input or output twice, for example, or if you left an dangling input or output, the materializer is going to complain. So theoretically, we would be able to just return a flow shape whose input is going to be the input of the balance stage and whose output is going to be the output of the merge stage. But this is not enough, since you can see that we have an unused value of which represents the worker. So we need to explicitly add it to a graph. And in the Java API, we need to do it explicitly for every input of the balance and every output of the balance stage and every input of the merge stage. So we're going to use an in-stream range it's a for loop basically, but in another approach. And now what we're going to say, well, first of all, we need to add the worker to the graph. Let's call it a worker stage. So you can see that like for every value of I, we're reusing the worker. So this is the same building block, but we need to create another instance of the worker in our graph. So this is the working stage. And now we need to connect everything together. So we're going to take the one of the outputs of the balance stage, number I, connect it to the worker stage, and then connect it to the one of the inputs of the merge stage. So this is the Java API, and actually if you did it in Scala, it would be a bit easier, because in Scala you would have this like magic arrow operator which would do all the adding to the graph and like putting it all together. So now we're able to use the balancer here. So we'll say balancer create. We have a parameter for concurrent files, and here we provide the process single file. Okay, so now we have our Cassandra instance running in a Docker container. We have an empty readings table. So let's just, and we need a main method to run it, for example. This is going to be fast. So let's now try to run it. The main method, as you can see, doesn't do anything fancy. It creates the actor system, it creates the configuration, and that's it. Here in the logs you can see that some of the lines were indeed invalid, and they are just logged, but still handled gracefully in the average computation. And now you can see that the values are actually there in Cassandra. Okay, so well, that's actually all I had. The time is up, so I will have time for questions afterwards. Just to recap, what you can do apart from what you've seen, you can use the graph DSL. We have actually used it to create a custom graph from the built-in blocks or from your own as well. You can also build your own flow so this is like even lower level of the API. I wrote a blog post about it. The links would be there at the end. You can actually use Alpaca, which is an integration layer for Akka Streams that lets you connect those to a number of external systems. So thank you for your attention. Under the QR code is the same link that is displayed below. This is basically a landing page with all the links to the source code, to the blog post, so feel free to visit it, and thanks. If you have any questions, I'm here.